All right, guys, so this week we're going to start our parametric functions. Some of you guys may have seen this right before we were let out of school, but we're still going to take the notes on it and do some assignments with that because parametric functions is something that we do use a lot in BC calculus or in physics classes. You might use parametric functions as well. So a parametric equation is an equation that's actually in two forms. So you have a function for x and a function for y, and your independent variable is t. Okay, so x and y now become dependent variables, and the independent variable is t. And they usually use t because in word applications or word problems, the t represents time. But it doesn't always have to be t. Just like when we do functions y in terms of x, we don't always use x as our independent variable. Sometimes we use t or theta or p or any other variable. You can do the same thing with parametrics. It's not always going to be t. It's just usually going to be t. So t doesn't really show up in the graph. It's not really an axis. It's more the order of the points and how you connect them. Okay, so as t increases, you have to connect the points in that order, where we're used to connecting points from left to right. Now, these graphs are not necessarily going to go from left to right because x is no longer the independent variable. So the one of the ways we can graph it is by doing our old school point plotting. So when you do point plotting, you have to pick values for the independent variable. So our independent variable is t, so we would just choose random variables or values for t as long as there's no restriction. Sometimes a problem might say t greater than or equal to 0 or t between -2 and 7. All right, so they might put a domain restriction on there, but if not, then basically t should be able to be all reals. So the first function is telling us that the x coordinates can be found by doing t squared minus 2t, and the y coordinates on the curve can be found by doing t plus 1. So I'm going to set up a table of t values. I actually set up t greater than or equal to 0, but that's not always going to be the case. So t is 0, 1, 2, 3, 4, 5. And then you can find the corresponding x and y values by plugging the t values into this. All right. And again, sometimes t could be negative in problems as well, but I just did this one where t is going from 0 to 5. So when you plot these points, you have to plot them and connect them in this order. So you plot the point 0, 1, -1, -2, 0, 3, 3, 4, 8, 5, 15, 6, and then you connect them in that order. So sometimes it's nice to number the points so that you know that they go in that order. Or we can also put arrows on the graph as well to show the direction of the curve. So when we plot it, we should be getting this. So we're starting at that point 0, 1. And then we go to our -1, 2. We've got 0, 3. All right, and we keep going this way. So this would be the direction of the curve. Right? And if we had t was negative values, it would have continued on this way. Okay, but the graph would have been connected in this order. All right, that's the key thing because we have direction and we have motion. So why do we use them? Okay, we use them usually to describe curves in the plane when one function won't do. So when we get these basic non-functions, okay, this would have failed the vertical line test in a regular function mode, but as a parametric, it doesn't because again, now x and y are dependent variables and t is the independent. And we use this a lot to describe a path because you can find two positions rather than just one, all right, where we're used to with just regular functions. So if we looked at this as a path, this curve, as t increases, so t is the independent variable, x first decreases. So what does that mean about the path? It means that the path of the particle is actually moving to the left. And then increases, all right, once you hit this t value. All right, and now the path moves to the right. And if we also wanted to look at the vertical motion, the path is actually always moving up. Right. And we talk a lot about rates of change in calculus. How do we determine whether a path is moving left, right, up, or down? By just looking at the function, not looking at the graph. And that's something that we will do when we start talking about derivatives and things like that. Okay, but this is something we've never seen. We've never connected graphs going to the left, and now we can. Okay, so if you want to move on to the next video.